How's it going, folks? Today we're going to be talking about the Hall effect. It's the moment you guys have all been waiting for, I know. It's exciting stuff. Basically, this is an effect, a phenomenon that was first described by Edwin Hall in 1879, and it has huge applications in our world today. So let's jump right into it, okay? Let's say we have a metal conducting plate. Let's call it copper for all intents and purposes, okay? And let's create a circuit out of this copper. Copper is a conducting metal. Let's give the side the positive end and the negative end. And let's run a current through it. And we all know, I'm sorry, Benjamin Franklin, that electrons are actually what carry current. They move. And so let's make an electron blue, okay? Electron is moving from the negative side to the positive side. It's moving this way, all right? And now let's expose this metal wire or this plate or whatever we have to a uniform magnetic field, okay? And let's have that magnetic field be purple. It's moving into the screen, into the plane of the board, okay? Like the back of an arrow. So everything is exposed uniformly to this magnetic field. And if we use our right-hand rule, I'll come on this side for that. We have a charge moving this way, and we have a magnetic field into the plane of the board. If it was a positive charge, it'd be moving down, but since it's negative, we flip it. Our negative charge is going to be forced to the top of our little metal plate. So let's draw that. It's going to experience a Lorentz force pushing it upwards. So after a quick moment, all of these negative charges, they're going to experience this force because they're moving this way, push to the top. And after a brief moment of time, what we're going to see is a buildup of negative charges on the top of our metal plate. And complementary to a buildup of negative charges at the top, we're going to see a buildup of positive charges at the bottom. And what does this look like to y'all? To me, it looks like something we've already talked about in physics way earlier in this year. That looks like an electric potential difference. And if there is an electric potential difference, there's a voltage there that we can measure. And in fact, we can, okay? So what is cool about this is, let's say we're going to continue having electrons move through this. Boom, boom, boom. Moving this way, all right? What keeps them from continually building up right there at the top? It is exactly that electric potential difference. They are subject to this electric field because these electrons, they don't want to be next to other electrons. The opposites attract, and so they want to be by these protons, these positive charges. So they want to move down. But as we previously described, they are also experiencing a Lorentz force pushing them up. When they reach that equilibrium, they just move across. So what we find is a relationship that the Lorentz force is equal to the electric field force. Force E equals force L. Let's write that out. Force E equals force L. The electric field strength, if you will, the force exerted on an electron is going to be equal to the force exerted on that same electron by the magnetic field. And what is force of an electric field? Force of an electric field is equal to the charge times the force of an electric field is equal to the charge of whatever we're talking about times the strength of the electric field. And that is going to be equal to the force Lorentz equals, we have our charge, the velocity of our charge, and then the magnetic field strength. Let's put those equal to each other and we get QE equals QVB. What do you guys notice? Yeah, we got Q's on both sides. Let's get rid of them. So I'm going to clean this up just a little bit to give us more room. We have E equals VB. Now we still want to get the voltage that we can measure, okay? And what does E, the electric field strength, it describes the EMF voltage over the width of our plate or wire, whatever we're talking about. And we can find that by, here, I'll use a different color. This is our width, okay? Let's do a little algebra. We can substitute the E for EMF over L equals VB. Let's multiply both sides by L, and we get the Hall EMF equals the velocity of our charge times the magnetic field times the length or the width of our conducting plate, in this case, our copper plate, okay? And what happens is that you can actually attach a voltmeter, let's use green for this, to each side, and you can measure that Hall EMF. It's going to be, have this relationship, Hall EMF equals the velocity times our magnetic field times the width of our wire or our conductor, our current carrying conductor, if you will. And it's cool, there are a bunch of different applications to this. You can find different things in your blood. This, the voltage when you connect a magnetic field to a blood vessel. It's very non-invasive. You can find a bunch of different properties with water or fluids carrying charged particles through a pipe. Or you can find the voltage across a wire, whatever you want. But all of this describes the Hall effect. The Hall effect, and it's a pretty cool thing. I hope you guys learned something new today, and I hope you enjoyed this video.